if you just close your eyes and imagine floating in absolute pitch black space, no up, no down, no stars to guide you, just an infinite void.
Right, complete sensory deprivation.
Exactly. In that void, if I tell you to move forward, well, the immediate problem you hit is, what is forward?
You can't know.
No, you can't. Without a single reference point, the very concept of direction just completely ceases to exist.
Yeah, it vanishes entirely.
Yeah.
You need to navigate or to even understand where you are in that kind of void, you have to build a spatial reality completely from scratch using geometry.
Right.
You literally need to invent a framework to define what a direction actually is.
Yeah.
And that invisible scaffolding is, well, it's exactly what we're exploring in this deep dive.
Yeah, and we are unpacking a highly specific, honestly fascinating set of notes today from day 27, vector algebra, direction cosines, and code.
Which is specifically pulling from Insert Chapter 10, sections 10.1 to 10.3 for those keeping track at home.
Yep. And our mission for you today, the listener, is to take that abstract textbook math and connect it to, like, the flight paths of rockets, the invisible energy fields of your Wi-Fi router, and fundamentally, the brain of artificial intelligence.
It does sound like a massive leap, I know. But the underlying theme in your sources today is how a single elegant mathematical concept can just entirely define spatial reality across vastly different disciplines.
So before we can fly a satellite or, code up an AI, we really need to understand how we map that pitch black void. We kind of have to go to the chalkboard for a minute.
We do. And we start with the absolute foundation, which is the vector.
Right.
A vector at its core encapsulates two pieces of information: the magnitude, which is how far you are going, and the direction, meaning which way you are actually pointing.
Just distance and heading.
Exactly. So to make this concrete, imagine a discrete point in a standard 3D Cartesian space. We'll just call this point P.
Okay, point P.
And it has three coordinates, right? Your standard X, Y, and Z. If you want to connect the origin point-like dead center at 0, 0, 0 to your point P, you draw a line.
And that line is your position vector.
You got it. That line is the position vector.
Now, the notes formalize this position vector with an equation, and it's written as vector r equaling x times I hat plus y times j hat plus z times k hat.
Right. The classic formula.
But Lev, pause there, because reading math out loud can sound like a foreign language. If you are listening to this and wondering what on earth the hats are about, how should we visualize those?
Yeah, that trips a lot of people up. Think of those hats as the pure essence of a single dimension.
Like the raw idea of a dimension.
Exactly. The X, Y, and Z numbers, those are the actual distances you travel. But the I hat, J hat, and K hat, they are the unadulterated directions of the axes themselves.
Oh, I see.
They're basically instructions. They say to you, move this far along the X, then move this far on the axis, and finally this far up the Z axis.
Okay, let's unpack this. We have our line drawn in 3D space, but we still need to know its length.
Right, the how far part.
Yeah, and the notes introduce the magnitude, which they evaluate using the Euclidean norm.
Which sounds incredibly intimidating, but the map here is really just the classic Pythagorean theorem.
Just a squared plus b squared equals c squared.
Exactly. But supercharged with a third dimension to handle 3D space. To find the total length of your vector, you just take the square root of your x distance squared plus your y distance squared plus your z distance squared.
Okay, so that gives us the how far part of the vector. But the which way part is where the day 27 notes introduce a really fascinating mechanism.
The direction cosines.
Yes. This brings us to direction cosines, which the notes represent with the letters L, M, and N.
Yeah, and those letters represent the actual cosines of three specific angles. So imagine your vector sticking out into space.
Okay, I'm picturing it.
Now measure the angle between that vector and the flat x-axis. We call that angle alpha. Then you do the exact same thing for the y-axis, calling that angle beta, and the z-axis, calling it gamma.
And the formulas to find these are beautifully simple.
Right, totally. The direction cosine L is just your x-coordinate divided by the total magnitude of the vector.
The distance we just found using the Euclidean norm.
Right. And then the cosine M is just your y-coordinate divided by the magnitude, and N is z divided by the magnitude.
So we're literally isolating the direction away from the distance.
Completely.
And this leads to the most crucial part of the math. A rule the notes call the constraint equation. It states that L squared plus M squared plus N squared equals exactly 1, always.
Always 1.
I want to push on this a bit because, equations on a page are one thing, but what does this constraint actually do for us practically? Why must it equal exactly 1?
What's fascinating here is that it acts as the ultimate balancing mechanism for reality.
How so?
Well, when a vector has a magnitude of exactly 1, we call it a unit vector. It has been stripped of all its length, leaving only its pure directional identity.
Just the pure which way?
Yes, by mathematically proving that the squares of these direction cosines always add up to 1, we guarantee that no matter how far a vector stretches, like whether it's across a room or across the entire solar system, its directional identity remains perfectly balanced.
Okay, let me try an analogy here to see if I am grasping the actual mechanism.
Go for it.
Imagine a sound mixing board, with 3 sliders. One for the x-axis, one for y, one for z. And the master volume represents our total directionality.
I like this already.
So the constraint equation forces that master volume to be locked at exactly 100%. If I push the x slider all the way up, telling the vector to point purely along the x-axis, the y and z sliders must automatically pull themselves down to 0 to keep that master volume at exactly 100%.
That is a brilliant way to visualize it. You basically have a finite amount of direction.
Right.
If you allocate more of your vectors heading toward the z-axis, you mathematically have to steal that directional focus away from the x and y-axis. The constraint equation distributes that finite amount of directionality perfectly across 3 dimensions.
So we have this perfect mathematical compass that works in theory. It gives us a universal language for pointing at literally anything in space, regardless of the scale.
Exactly.
But how do we actually use it? I mean, how do we take this chalkboard math and use it to prevent a multi-million-dollar piece of hardware from tumbling into the atmosphere?
Well, mapping abstract vector properties to physical architectures is quite literally how we build our modern world. In aerospace engineering, specifically flight dynamics, vectors are the literal backbone of navigation.
Right, because you need to know where you are.
Yeah, a position vector defines a satellite's center of mass relative to the Earth's core.
But just knowing where the center of the satellite isn't enough, is it? I mean, you need to know how the machine itself is physically oriented. Is the communication dish facing Earth, or is it accidentally pointing out into deep space?
Exactly, and that orientation is what we call the spacecraft's attitude. And we define that attitude using our pitch, roll, and yaw angles relative to an inertial reference frame.
So pitch is tilting the nose up or down, yaw is turning left or right, and roll is rotating along the main axis.
Spot on. And the sources highlight that defining these angles with direction cosines is absolutely critical for thrust vectoring and orbital maneuvers.
Here's where it gets really interesting for me. I always just pictured a spacecraft's onboard computer running a simple command, like turn left.
Right, like driving a car.
Yeah. But it is constantly running these direction cosine calculations, isn't it?
Oh, constantly. It is a continuous verification loop. The onboard computer is constantly measuring its orientation sensors,
Yeah.
calculating its L, M, and N values, squaring them, and adding them together.
And checking for that constraint equation.
Exactly. If that equation equals 1, the computer knows its orientation data is accurate. If it squares those cosines and gets a 1.0002,
Then something is wrong.
yeah, the computer instantly knows a sensor is drifting or the satellite is experiencing an unexpected torque.
So the math literally forces a reality check. It is basically the satellite's internal gyroscope talking directly to the universe.
That's a great way to put it.
If you want to fire a thruster to change your orbit, your direction cosines dictate the exact angle of that physical force. If they are misaligned even slightly, your rocket pushes you sideways.
And if we connect this to the bigger picture, we see that same continuous reliance on direction cosines when we move into electronics and RF engineering.
Really?
Oh, yeah.
Yeah.
We leave behind massive chunks of metal moving in a vacuum, and we enter the realm of invisible wave propagation. Vector fields define the physical path of signals.
Okay, the sources specifically mention the Poynting vector here, and that's spelled with a Y, by the way, not an I.
Right, named after John Henry Poynting.
Right, so it dictates the directional flow of electromagnetic energy. Basically, your Wi-Fi router, the cell towers outside your window, they are pushing energy through space, and the Poynting vector governs where that energy actually travels.
And the precise direction matters immensely here as well. The notes specify that direction cosines are used to calculate the spatial polarization angles of RF waves transmitting from a phased array antenna.
Now, a phased array antenna is fascinating because it doesn't physically move.
Not at all.
Right, an old-school radar dish has to physically spin its heavy metal head to point a signal, but a phased array is completely flat. It uses complex math to steer an invisible beam of electromagnetic energy electronically. How do direction cosines achieve that without moving parts?
By adjusting the timing or the phase of the signal, leaving hundreds of tiny individual antennas on that flat panel.
Oh, wow.
Yeah, to steer the combined beam to a specific point in the sky, the system calculates the direction cosines for that target. It then uses those exact L, M, and N values to determine precisely how many microseconds to delay the signal from each tiny antenna.
So they fire at slightly different times.
Exactly. The waves interfere with each other in midair, canceling out in some directions and adding together in the specific direction dictated by the cosines.
That is wild. The physical universe is incredibly strict. Whether it is a physical rocket engine blasting fire or a flat antenna silently delaying radio waves by a microsecond, the physical universe obeys the exact same direction cosine rules to navigate energy through 3D space.
The rules that govern massive physical objects apply perfectly to massless electromagnetic waves. It's beautiful.
It really is.
But what happens when we push the math even further? What happens when we remove physical space entirely and apply this geometry to human thought?
Okay, this is the part of the notes that feels straight out of science fiction. We enter the realm of computing and software, specifically machine learning.
Right.
When dealing with physical space, we use 3 dimensions, x, y, and z. But in computing, the notes tell us that data structures are represented as n-dimensional vectors.
And the letter n just means any number. In the physical world, we are trapped in 3 dimensions. But in a computer, an array of data can have 3 dimensions, or 300 or 3,000.
Wait, I have to stop you there to make sure I'm visualizing this right. Wait, so when an AI is learning human language, like reading massive amounts of text, the sources say it uses word embeddings. Is it essentially treating words like dog and cat as if they were literal satellites floating in an n-dimensional space? If they have similar meanings, does that just mean their direction cosines are pointing in the same direction?
That is precisely what it is doing.
That's crazy.
I mean, AI does not have a brain. It doesn't understand language, feelings, or dictionary definitions. It only understands numbers. When we feed a word into a machine learning model, the model translates that word into a vector, a coordinate in a massive multidimensional space.
Okay, let's unpack the dimensions then. If x, y, and z are physical directions like up, down, and left, well, what are the axes in an AI space?
In AI, the axes represent abstract semantic features. Imagine an axis for domestication, another axis for fluffiness, another for size. The word dog might have a very high positive value on the domestication axis, and maybe a medium value on the size axis.
So dog is located at a specific coordinate across, say, 500 of these different feature axes.
Exactly.
And cat is located at another coordinate. But if I introduce the word wolf, its vector would be way down at the negative end of the domestication axis, pulling its coordinate to an entirely different part of the space.
Yes, the vector for wolf shifts dramatically. Now, how does the AI know mathematically that a dog and a cat are closely related concepts, but a dog and a wolf have a different relationship?
How?
It draws a vector from the origin to dog and another vector from the origin to cat. Then it literally calculates the direction cosines for both vectors to find the geometric angle between them.
And the sources introduce this as cosine similarity.
Yes.
It utilizes the dot product and our direction cosines. So how does the dot product actually calculate that similarity?
The dot product is a mathematical operation that essentially multiplies the aligned components of 2 vectors. When you combine the dot product with the magnitudes of the vectors, you are left with a pure cosine of the angle between them.
Just the angle.
Right. If the angle is very small, meaning the vectors are pointing in almost the exact same n-dimensional direction, the cosine similarity approaches 1, and the AI concludes mathematically that the words have highly similar meanings.
That is absolutely mind-blowing. So if the angle is wide, the words are unrelated. If the vectors point in completely opposite directions, giving a cosine of -1, the words are antonyms. AI fundamentally understands human language through the geometry of direction cosines.
Yes. The beauty of n-dimensional space is that the math doesn't break down when you go past 3 dimensions. The Euclidean norm equation just gets longer. You are taking the square root of 500 squared values instead of 3.
But the core rule stays the same.
Exactly. The constraint equation still holds its foundational truth. We are just using geometry to map meaning instead of physical location.
Wow. We've mapped out the physical universe in the minds of AI, but how does a learner actually build and control these vectors on their own computer? Because the Day 27 notes don't just leave us with theory, do they?
No, they don't.
They include a 10-minute code action script to make this real.
Theoretical math is only half the battle,
Mm.
honestly. To truly grasp these concepts, you need to manipulate them. The notes provide a practical script using Python, which is the standard language for data science and AI.
Right.
Specifically, it initializes vectors using NumPy arrays to programmatically extract their magnitude and direction cosines.
So what does this all mean when we look at the actual code? Because the notes state that the script initializes vectors as 1D NumPy arrays. I feel like that terminology could really trip someone up.
It definitely can.
If we are talking about 3D spatial concepts or massive n-dimensional AI concepts, why are we representing them as a 1D NumPy array?
This raises an important question, and it's a very common hurdle when moving from a math textbook to a code editor. It's the distinction between spatial dimensions and data structure dimensions. Okay, lay it out for us. When we say a space is 3D, we mean it has an x, a, y, and a z-axis. It describes a volume.
But in programming.
In programming, an array is just a list of numbers in the computer's memory. A 1D NumPy array simply means it is a single, flat list. It is one-dimensional in its data structure.
Oh, I get it.
You don't need a 3D cube of memory to hold 3 coordinates. A single 1D flat list can hold the numbers 5, 10, and 15, representing our x, y, and z coordinates. So the array itself is a 1D list, but the data it contains defines a 3D spatial vector.
Okay, that makes perfect sense now. It's just a flat list holding spatial instructions.
Exactly.
And the Python script takes that list, automates all the heavy lifting of the Euclidean norm formula, like the squaring and adding of all those numbers, and just spits out the exact direction cosines.
It automates the algebra so you can focus on the geometry. And the notes heavily encourage taking this further by exploring a 3D simulation. They suggest visually exploring how tweaking these parameters in the code affects the spatial orientation of a vector on screen.
And seeing the vector actually swing across a simulated screen when you change a single value in that 1D array. I mean, that is where the concept really locks into your brain.
Oh, absolutely.
It bridges the gap between a static equation on a textbook page and the dynamic reality it actually represents. You are doing on a small scale exactly what a rocket engineer does when they send a thrust vectoring command.
You're quite literally commanding space through code.
All right, let's bring this all together for you. We started this journey today with a very simple concept, basically a point in a pitch black void defined by an x, y, and z coordinate.
Yep.
We realized that navigating that void is governed by a strict, unyielding mechanism, that constraint equation, where the finite directionality of L squared plus M squared plus N squared must always equal exactly 1.
And from that single geometric truth, we saw how it expands outward. It forms the continuous verification loop that keeps a multi-ton satellite from tumbling out of orbit.
Right.
It creates the precise microsecond delays that steer invisible electromagnetic waves from phased array antennas.
And most incredibly, at least to me, it strips away physical space entirely to map human language. It allows artificial intelligence to mathematically prove that the words dog and cat have similar meanings by simply measuring the angles between them in a massive n-dimensional void.
It really is incredible.
Mastering this one piece of day 27 theory doesn't just help you pass a math test. It literally gives you the nuts and bolts, the skeleton key to multiple cutting-edge industries.
It is the foundational language of spatial reality, whether physical or digital. But there is a lingering idea here, something born directly from combining these sources, that kind of changes how we view the future of that reality.
What's that?
Well, we established that direction cosines perfectly map the physical trajectory of a satellite in 3D space.
Right.
And we established that those exact same equations perfectly map the abstract meaning of human language in n-dimensional AI space. The math operates identically in both domains.
It's the same math.
Exactly. So what happens when we start using those exact same n-dimensional AI vectors to discover new physical realities?
Wait, what do you mean?
We are already seeing AI map the complex folding structures of proteins using high-dimensional geometry. The math strongly suggests that the boundary between our physical universe and artificial intelligence isn't a hard barrier at all. It is literally just a matter of adding more dimensions to the equation.
Man, that is wild. We started by imagining you floating in an infinite void without a single reference point. The vector is the light you turn on to finally see the shape of the room.
Beautifully said.
The math gives you a direction to move. But with n-dimensional vectors, the room you are exploring might be larger and definitely stranger than we ever thought possible. Keep exploring those coordinates, everybody. We'll catch you on the next deep dive.